Good evening. Tonight's presentation, we're going to hear a discussion of what gravitational waves are and how they are used to observe the universe in a new way. We'll hear the description of the incredibly sensitive instrument known as LIGO, Laser Interferometer Gravitational Wave Observatory, its history, and how it functions. Sources of detectable gravitational waves are some of the most violent, energetic events in the universe, from the earliest moments after the Big Bang to the supernova deaths of stars to the merger in binary systems of neutron stars and black holes. Tonight's presentation is a collaboration between Amber Stuver and Professor Jerry Dunifer from the Department of Physics and Astronomy at Wayne State University. A little bit about Amber Stuver. She is currently an assistant professor in the Department of Physics at Villanova University. She got a PhD degree in 2006 in physics from Pennsylvania State University, working on burst gravitational wave simulation and data analysis methods. She was formerly at LIGO Livingston Observatory at Louisiana State University. She has been a member of the LIGO scientific collaboration since 1999. Her professional life is spent working on LIGO research, teaching, and doing service for the American Physical Society and the American Association of Physics Teachers. Presenting tonight's presentation on LIGO and the detection of gravitational waves is Dr. Jerry Dunifer, Department of Physics and Astronomy, Wayne State University.
Thank you, Mark. And good evening, ladies and gentlemen. Can everybody hear me in the back?
They can't, they're deaf.
Okay. So as was mentioned, this talk is a collaboration between myself and Amber Stuver from Villanova University. So this is a picture of Amber. She's been a member of the LIGO scientific collaboration since 1999, and she provided approximately 2/3 of the slides, which I'll be showing this evening. So, 34 days ago, back in October 3rd of 2017, in Stockholm, at 11:15 in the morning, they announced the 2017 Nobel Prize in Physics. And it went to 3 Americans, and you see them here. From left to right is Rainer Weiss, and then Barish and Kip Thorne. And they were awarded this prize, as indicated, for decisive contributions to the LIGO detector and the observation of gravitational waves. Is it possible to shrink the picture just a little bit so we can get everything on screen?
Probably.
I don't know how to do that. Okay, it's not critical.
Sure.
Okay, thank you. Okay, well, it's about the same, but I think it'll be good enough for most of our purposes. So anyway, the Nobel Prize was awarded for these 3 gentlemen and their decisive contributions to the LIGO detector and the observation of gravitational waves. So that is the topic which I'm going to be talking about this evening. It was September 13 and 14 that Kip Thorne came to Michigan, and he gave a couple talks. One was in Ann Arbor, and one was down on the Wayne State campus at my invitation. So it was nice to have him for a few hours on the campus talking to us. So we're going to start with Amber's contribution. Back in 1915, Albert Einstein introduced his general theory of relativity. This is a theory which describes the most fundamental things in nature, such as space, time, motion, and gravity. According to the theory, gravity is not actually a force, but can really be pictured as a curvature or a bending of the four-dimensional space-time continuum in which we live. Now, according to the theory, it is possible to set up waves which travel through space, which are due to the motion of mass. It is mass which gives rise to the curvature of space, and let me illustrate that in the next slide.
Einstein's concept was to look at the body's influence on the space they're embedded in. And so in Einstein's picture, a massive body makes a depression in the space-time around it, so that other bodies following their natural paths tend to be attracted to this depression.
So that is one way of representing this curvature of space, which is due to the presence of mass. This is another way of representing it, in which this is sometimes called the trampoline model, in which we use a flat two-dimensional space to represent the three dimensions in which we live, and then depressions in that space are used to represent curvature. So in this slide, we have the Sun and Earth system, and the Sun with its larger mass produces a larger depression, and the Earth itself a smaller depression. Now, if, according to the theory of general relativity, if a mass is made to accelerate, it produces ripples in space-time. These ripples travel away from the mass at the speed of light, and these ripples are in fact the gravitational waves. Einstein first suggested that there can be gravitational waves from his general theory of relativity in the year 1960. However, he made the statement that the oscillations of space would be so small that there would be no way of really detecting them. Fortunately, thanks to the three Nobel laureates, Einstein was disproved in that regard. Now, these gravitational waves are very similar to other waves in that they have a well-defined frequency, wavelength, and velocity. But different than other waves is they represent a physical oscillation of space itself, which makes them a very interesting phenomenon. So the next slide that I'm going to show you is two objects in close proximity to each other, which are orbiting around each other. The circular orbits represent an acceleration which produces gravitational waves, and these waves carry energy away from the orbiting bodies. So as they lose energy, they're going to be moving closer together, moving faster and faster as they revolve, and generating stronger and stronger gravitational waves until they finally merge. So here you see the two orbiting bodies and the gravitational waves which are traveling outwards. As they get closer and orbit faster, the frequency of the waves goes up, and eventually they merge, and the gravitational waves go off at the speed of light. Let me just see if I can get that once more. Gravitational waves formed by two objects in close proximity, rapidly revolving around each other. So those could have been two black holes which merged into a larger black hole, which is the nature of the first gravitational wave observation which took place. So just how large are these waves when they get down here to Earth? Well, the observations which have been carried out for the last several months, we see black holes orbiting around each other and merging, but at distances of more than 1 billion light years. So by the time the gravitational waves get to Earth, traveling at the speed of light, some billions over 1 billion years have gone by, and the waves are quite weak when they get here. And so the physical oscillations of space are indicated in this slide, corresponding to something like 10 to the minus 18 meters. So to give you a feeling for what that size is, if you take an ordinary human hair and you get out your vernier calipers or micrometer calipers and measure the diameter, typically it's about 4/1000th of an inch. 1/10,000th of a meter, or 10 to the minus 4 meters. If you look at a single atom, that atom has a diameter which is about 1,000,000 times smaller, or 10 to the minus 10 meters. And if you look at the nucleus of that atom, that's another 100,000 times smaller, getting down to 10 to the minus 15 meters. And finally, if you look at the size of the gravitational wave oscillation, that's another factor of 1,000 times smaller, the 10 to the minus 18 meters. So what do these waves look like? The gravitational waves are transverse waves, meaning that the oscillations of space are in a direction perpendicular to the direction in which the wave is traveling. So if you look at the picture on the left, what we see here is a gravitational wave, which you can picture as traveling into the screen, perpendicular to the screen, and the oscillations of space take place in the plane of the screen. So there are vertical oscillations, as indicated. Space stretches and then is compressed, expands and compressed vertically. The same thing is happening horizontally, but 180 degrees out of phase. So that when we get a stretching in the vertical direction, we get a compression in the horizontal direction. So that is the nature of the gravitational wave, the type of oscillation which is taking place spatially as the wave travels past. So how does one measure something like this, which is incredibly small, this 10 to the minus 18 meters? Well, that is where the observatory LIGO comes in. Again, LIGO stands for Laser Interferometer Gravitational Wave Observatory. So it makes use of a Michelson interferometer, which was invented by Albert Michelson back in the 1800s, an American physicist, played a prominent role in 1887 in the Michelson-Morley experiment, in which they tried to measure the absolute motion of the Earth through space. That experiment failed, but it ultimately led to Einstein's special theory of relativity. So this is the way in which this functions, this Michelson interferometer and LIGO. So we see a laser source, sends out a beam of infrared radiation at a beam splitter. It splits into two perpendicular beams. Encountered mirrors, which are 4 kilometers away. They're reflected back on themselves and are recombined and go to a photodetector, which is here. Now, as the gravitational wave goes by and space expands and contracts a little bit along the two arms of the interferometer, these waves are alternating back and forth between in phase and out of phase, which you see over here at the detector. Now, this in fact is highly exaggerating what happens. It's actually much smaller than that. The detector is arranged so that the two light beams are originally exactly out of phase, so you get no signal at the detector, and they're looking for small changes away from that as the gravitational wave goes by. Okay, this is another view of LIGO in just a little more detail. So this is LIGO right here. We have the laser source, which puts out about 20 watts of power in the infrared. Goes through power recycling, boosting the power to about 700 watts. Encounters a beam splitter, which sends one beam straight ahead and another one off at right angles. The additional thing which is shown here are two more mirrors. This is the mirror, and this mirror down here was shown in the previous slide, but there's an additional mirror and an additional mirror here. These are called test masses, but they're really the mirrors with a mass of about 40 kilograms. This combination of mirrors is known as a Fabry-Perot cavity, and it has a property that the laser beam can go in through the mirror, but then bounces back and forth more than 100 times before it eventually comes back out again. So this increases the effective path length of each of these arms by over a factor of 100. And in the process of doing this, the effective power which is circulating back and forth is increased to about 100 kilowatts. Ultimately, the two beams come back, are recombined, and go down to our photodetector. Now, there are two of these antennas in the United States. There's one down here at Livingston, Louisiana, called L1, and there's one at Hanford, Washington, at this location up here called H1. So Hanford is the location where they used to make plutonium for the atomic bombs down on the banks of the Columbia River. Now, they've drawn in here a dash line, and the travel time for light to travel along that dash line between the two detectors is 10 milliseconds, 10 thousandths of a second. Gravitational waves travel at the same speed as light, so it also takes gravitational waves traveling that direction 10 milliseconds to travel from one to the other. So if we have a gravitational wave coming in this direction, it encounters L1 first, and then 10 milliseconds later, it encounters H1. On the other hand, if the gravitational wave is traveling in the opposite direction, it encounters H1 first, and then L1 10 milliseconds later. And if the gravitational wave is coming in perpendicular to that dash line, it encounters both detectors at the same time. So by looking at the difference in the arrival time of the two gravitational, or of the gravitational wave at the two detectors, we can get a rough indication as to where in the sky the gravitational wave is coming from. And the other part of this figure is in the upper right here, which shows the noise characteristics of the electronic detectors as a function of frequency. So we're looking at the frequency from 20 hertz, 20 cycles per second, up to about 2,000 hertz. And vertically, we're plotting the strain noise. The strain is defined to be the fractional change of this distance, the 4 kilometer distance. The fractional change, the change in that distance divided by the original distance. And in fact, this turned out to be very, very small when we're looking at the noise level. We're down here 10 to the minus 21, 10 to the minus 22, 10 to the minus 23. So this is the noise seen at the two observatories. There's some spikes here which you can forget about. That's due to certain resonances within the instrument. But the minimum noise is around 200 hertz or so. Gravitational wave signals which have been detected have been in the range of 10 to the minus 22 up to 10 to the minus 21 in the strain, which is considerably above the noise level and therefore readily detected. So again, this is the location of the two LIGO observatories, Livingston, Louisiana, and Hanford, Washington. So just a few more details about LIGO. It's the largest and most expensive project that's been funded by the National Science Foundation. About $1 billion has been spent. There's more than 1,000 scientists and engineers who have worked on the project, of whom I know 2, including Amber. They come from 80 different institutions and 16 different countries. Again, the length of the arms, 4 kilometers. The laser source is a solid state source, a neodymium YAG laser that produces infrared radiation with a wavelength of 1064 nanometers and a power output of 20 watts. These Fabry-Perot cavities I talked about increase the effective length of each of the arms by 280 times. Again, the effective laser power between the mirrors is 100,000 watts. So the effective length of these arms with the multiple bounces back and forth between the mirrors is more than 1,000 kilometers. The initial run was done from 2002 to 2010 with no detections. They weren't really expecting any. And then they shut down for about 5 years, did a considerable revamping of the instrument, increasing its sensitivity, and began again in September of 2015. And with the new run, it's often called Advanced LIGO. And within 3 days of starting it up, with the sensitivity increased by more than a factor of 10, they detected their first incoming gravitational wave. Now, the gravitational wave, again, is produced by the bulk motion of mass, can give us information which electromagnetic waves alone cannot. So, for example, in a type 2 supernova explosion, in which the core of the star is undergoing an implosion, we cannot see that with electromagnetic waves, but it might be possible to do that with gravitational waves. Objects like black holes, which do not give off electromagnetic waves, can be seen using gravitational waves. The gravitational waves that pass through everything. Nothing can block a gravitational wave from reaching the Earth. And this allows us, for example, to look back to the very beginning of our universe at the Big Bang, or within 10 to the minus 35 seconds of the Big Bang. On the other hand, with electromagnetic waves, one can only see back to about 300,000 years after the Big Bang, when we encounter the cosmic microwave background. So here is the first detection. This occurred on September 14, 2015, and was the result of 2 black holes in space orbiting around each other and coalescing and merging into a single one. And here you see the data. It was seen first at the Livingston site. We're plotting the strain vertically. And this is a fairly short period of time. This is about 0.2 of a second total. So to begin with, you see mostly noise over here. And then as you go further in time, you see this oscillatory signal rising out of the noise and then undergoing a fairly sharp cutoff. So this type of a signal in which the amplitude builds up fairly rapidly, the frequency builds up fairly rapidly, and then there is a sudden cutoff. This is often called a chirp. Now, let me show you what was seen 7 milliseconds later at Hanford. So they say essentially the same signal, delayed 7 milliseconds in time. Now, here is something which should knock your socks off. During the last 1/10 of a second or so during this merger, there was a tremendous amount of power which is being put into the gravitational wave, taken from the orbiting black holes, such that the amount of power carried away by the gravitational waves was something like 50 times the luminosity of the universe. That is, if you take all the stars in the entire universe and add together the total power they are radiating into space for a short time, 1/10 of a second or so, this event was putting out 50 times more power than that. That should knock your socks off. If not, then your shoelaces are probably a little bit too tight. Now, one can take the general theory of relativity and try and fit the theory to the data which was observed. And that is what is shown here. Now, there's a light blue curve, a smoother curve without the noise. Over here, a yellowish curve, smoother curve without the noise. So this is the fitting of the theory to the observational data, and it's almost perfect. And in the process of doing this fitting, one can learn a number of things. One can learn the initial masses of the black holes. One can learn the final mass of the black hole that they merge into. One can determine the spins of the black holes involved. And one can determine the distance. The distance is simply determined by the strength of the signal, how large it is when it arrives here at Earth. Now in the next slide, I'm going to show you a different way of displaying this data, in which I'm plotting vertically the frequency as a function of time. And since the frequency is going to be in the audio range, which the human ear can hear, we're also going to put in an audio tone that you can listen to and you can hear the chirp. What it's going to sound like mostly is simply a fairly loud thump at the time the two black holes merge. So that thump that you hear at the end is the instant the two holes merge into one. That is our chirp. I'm going to play the same thing over again, but we're going to boost the pitch of the audio tone to a higher frequency so it's a little bit easier to hear. Okay, so here you see the strain signal, and then frequency between about 32 and 512 plotted vertically as a function of the time. And again, the whole thing is over in just 0.2 of a second or so. Okay, next I'm going to show you an animation which was calculated from the general theory of relativity. Since this happens so fast, things are slowed down by a factor of 100. So these are the two black holes which merged. These white specks you see in the background are stars, which are further back, and the light from the star is being deflected around considerably by the strong curvature of space in the vicinity of the black holes. As we get close to the merger, we're going to slow time down even more.
What are their sizes?
I can tell you the masses and the sizes.
About 10 miles across?
They are going to be, the diameter is directly proportional to the mass. Probably tens of miles, something like that. In the ballpark of tens of miles in diameter, maybe 100 miles. Something like that. I don't have the exact size. Now looking at the difference in the arrival times at the two sites, one can get a rough estimate as to where this event happened in space. So this is the celestial sphere inside of it. And doing analysis of the data, we can say that the event happened somewhere inside this area indicated in colors. The outer contour line in pink is a 90% confidence level. So inside of that pink contour line, we're 90% sure the event happened somewhere in there. It's about 600 square degrees in the sky. So it's not real well localized, but we know roughly where it was. And then, on December 26th, Boxing Day, 2015, the scientists working on LIGO, I got a Christmas present. There was a second signal which was seen, and here we're plotting the frequency vertically as a function of the time horizontally at Hanford and at Livingston. So it's the same type of a chirp signal with the frequency rapidly building up, and then a sudden cutoff, which you see there. Here's an audio. I'm going to compare the two signals on the two dates. September, December, September. And we're going to do it again with an increased pitch. Okay, so those are the first two gravitational waves to be detected. I'm going to show you another animation now, again that was calculated using the general theory of relativity for the second detection. Now the signal lasted quite a bit longer, and so again it happens very fast, and so we're slowing time down. In this case we're slowing it down by a factor of 28. So here we go. So here are the two orbiting bodies. This is the second signal. So the strain is plotted, so you see the strain oscillating, units 10 to the minus 21. The frequency is going up, frequency increasing. We're getting closer, they're orbiting faster, the gravitational waves are stronger, they're going faster and faster. And here it comes. And they merge. And once again, the merging shown even slower in time. So this was a gravitational wave event number 2. Oh, let me go back. Not so much fun, we'll just do it again. What I wanted to show at the end is the group that did the calculations, which you're seeing displayed here. Kip Thorne was a major driving force in putting this group together, a fairly large comprehensive group from a number of different universities and research sites, which did the calculations, rather complex calculations, on big banks of computers. So here it is. It's called the Simulating Extreme Spacetimes SXS Project, due primarily to Kip Thorne. So again, looking at the delay time between the gravitational wave arriving at the 2 sites, we can somewhat localize where it occurred out in space. So that was the second event of December 26th. This was the first event of September 14th. And now, knowing the masses of the black holes involved, we can put them on a chart here. So we're plotting mass vertically. This is solar masses, so in terms of the mass of our own sun. In the lower left down here, they show 22 different black holes which have been identified. These were identified by X-ray studies using X-ray satellites in orbit around the Earth. Looking at X-rays emitted by very hot material which is falling into the black hole from the accretion disk which is swirling around it. And as you see, using that method, they found black holes with masses from about 5 times the mass of the Sun up to about 16 times the mass of the Sun. 5 to 16. The gravitational waves have found rather larger black holes. So the first merger I reported ended up with a black hole of 62 solar masses, and the second one ended up with a black hole just a little bit over 20 solar masses. Let me mention that the way these are designated is with GW for gravitational wave, and then the date of the observation. So this was observed on September 14, 2015. Now there's a third one which is indicated over here to the right. That is not on the official list, but there's a good possibility it is real. The signal to noise ratio was quite poor in that case, and they're not 100% sure it wasn't some artifact in the noise, or was it actually real? Well, a statistical analysis indicates that this probably happened with an 85% probability, but there's still a 15% possibility that it was just in the noise that was present at the time. But probably it happened, so we're going to assume at this time that it was. So we're going to leave it there on that graph. Now, if we had more of these gravitational wave observatories, we could do a better job of localizing where in space the gravitational waves are coming from. And in fact, there are more than just the 2 LIGO sites. So these are the 2 I've been talking about here at Hanford and at Livingston. But there are other ones scattered somewhat around the Earth. There's one in Germany called GEO 600 that's operated by the British and the Germans together. It's a smaller version of LIGO. The arms are 600 meters in length. And it was operational when the two gravitational waves were detected at Hanford and Livingston, but it didn't have sufficient sensitivity to detect them. There's another one called Virgo, which is in Italy. Now, when this slide was made, they said it was under construction. It has since been put into operation, so Virgo is now operational. It has arms which are 3 kilometers in length, operated jointly by the Italians and the French. And it was operating during the last 2 gravitational wave events, which I'll talk about just a little bit later. Kagra, over in Japan, is under construction. It's an underground observatory, and they're going to cryogenically cool the mirrors. It also has arms which are 3 kilometers in length. It's expected to become operational either late 2018 or early 2019. And one has also been proposed for India, but I'm not aware that any construction has started on that yet, as far as I know. So, looking at these signals which we've seen, there's a number of questions that one might ask, and perhaps additional information we might learn from them. We can ask, is general relativity the correct theory of gravity? So far, it has met all the tests that have been given, but this generation of gravitational waves is sort of an extreme test, so we will see. How does matter behave under extreme conditions? For example, in neutron stars. What is the equation of state of a neutron star? How does the pressure and density and temperature depend on each other? And down here, do compact binary mergers cause gamma ray burst? And I'll say a bit more about that a little bit later. How bumpy are neutron stars? We believe that the surfaces of neutron stars are solid, and they're very strong, and they can support mountains which are 2 or 3 centimeters in height. That's pretty high for a neutron star. Spinning neutron stars with mountains like that should give off gravitational waves, as we might see someday. Is there a primordial gravitational wave left over from the Big Bang? Do intermediate mass black holes exist? We know they exist up to 60 or so times the mass of the sun. We know there are supermassive black holes, which have masses of millions or billions times that of the sun. But are there intermediate ones with maybe 10,000 or 100,000 solar masses? Well, these kind of observations may tell us someday. Okay, so that is the first part of my talk, and that is a contribution from Amber. So now I'm going to do an update of what has happened since she put this talk together.
Jerry, before you do, can I
Yes.
ask a question about 7 or 8 slides back?
Yes.
There was a video of the gravitational wave detection against the background with some kind of static. Could we go back to that slide?
We can go back. You want to go back 7 or 8 slides?
I think just the previous, or one right before.
This one.
Yeah. So,
Yeah, those other streets that you see there are noise.
So the static, that's what I was going to ask. Is the background exclusively just noise?
Yeah, this is noise.
Okay.
So we're looking at the function of time, we're looking at frequency, and for these different frequencies, we're seeing noise. So the noise is present over a broad range of frequencies.
Okay, so is that like Gaussian? I mean, is it like the same sort of distribution of noise that you've seen?
I don't have the information on the distribution of the noise.
Okay.
It's a good question.
I'm just wondering, you know, how do you
I'm sure they've been very well studied, because that's exactly what they want to do, is maximize the signal to noise ratio. They want to get the noise as low as possible. So I'm sure the scientists there have a very thorough and complete understanding of the nature of the noise and the various sources of the noise.
Okay, and the supercooling will help with that, right?
cooling the mirrors certainly should help.
Thank you.
Okay, so this is going on now to my contribution, part 2, Advanced LIGO Run 02, which occurred between November 2016 and August 2017. So it came to an end fairly recently. The Advanced LIGO was shut down between February and November 2016 to make improvements. So the data I've shown you so far correspond to Run 01. And then it was shut down for several months to increase the sensitivity. And then they started with Run 02. And during Run 02, they detected 2 more black hole mergers. They also detected the first merger of 2 neutron stars, and other astronomers around the world, looking with a variety of telescopes, followed that event after the merger with a broad spread of different frequencies of the electromagnetic waves, anywhere from gamma rays down to visible light down through radio waves. When I was driving Kip Thorne back to the airport to catch a flight back to the West Coast, he commented that during Run 02, they were seeing approximately 1 gravitational wave event per month. Now, Run 02 goes for about 10 months there, but they've only reported 3 so far. So there are probably several more that they've detected and will be reporting sometime in the future. At the moment, Advanced LIGO is shut down for about a year, so they can make further improvements and further enhance the sensitivity. So I made a table here which lists all 6 of the gravitational wave events which have been detected to date. Most of these are black hole mergers, and these are in chronological order. So this is the event. These are the masses. Second column gives the masses of the black holes that were involved in terms of solar masses. Next column gives the final mass. For example, looking at the first roll across there, this was the first event seen back in September of 14. Gravitational wave seen September 14, 2015. The 2 black holes had masses of 29 and 36 times that of our sun. They combined into a single black hole with a mass of 62 solar masses. Now what's interesting is if you add the initial masses together, 29 and 36, you get 65, but you end up with 62. So the next column tells you the loss of mass. In this case, 3 solar masses simply disappeared. Where did it go?
Gravity waves.
That's right, gravity waves. It's the most famous formula in physics, thanks to Einstein, E equals mc squared. Energy is equals mass times the square of the speed of light. It is possible to convert mass into other forms of energy, and in this case, 3 solar masses worth of mass was converted into the energy carried away by these gravitational waves.
Very quickly.
And then the last column gives the distance in billions of light years. So the last 2 events, which I have listed down here, Virgo was also in operation and enabled us to pinpoint much more closely where the events were. This event was a black hole merger. At the very bottom one, if you can see it, corresponds to the merger of 2 neutron stars. So they had masses of 1.3 and 1.5 times that of our sun. They combined into an object with 2.74 solar masses. It is not known what that final object is. The general theory of relativity allows you to calculate an upper limit to the mass of a neutron star. And that turns out to be about 3 solar masses. And 2.74 is very close to that limit. So either the 2 neutron stars merged into a massive neutron star, or they may well have merged into a black hole. We don't know at this time. The mass loss is about 100 times smaller than it was for the black hole mergers, which would make the signal about 100 times weaker, but the neutron stars were about a factor of 10 closer, 130 million light years away, and that makes the signal 100 times stronger. So if you include the loss of mass, but how close they are, turns out the signal is still about the same strength as was seen from the merging black holes.
In the last case, also a lot of the energy was radiated as electromagnetic radiation also.
That's correct, yes. With the merger of the neutron stars, there was a lot of electromagnetic radiation as well. But the gravitational waves carried away the bulk of the energy. So, just putting them all together, this is what the signals look like. These are the strain signals, the spatial oscillations associated with each of the first 5 mergers of black holes that have been detected. What I was calling the second detection here is the longest last, and they have data which goes about 1.7 seconds. And now this is the same type of graph I gave you before, and now we can add 2 new ones. So these are the latest 2 mergers which were detected, producing a black hole with a mass a little less than 50 solar masses, and one a little greater than 50 solar masses. So this is Virgo over in Italy. This is what it looks like, an aerial view. And these are the 2 perpendicular arms, each 3 kilometers in length. And the last 2 events I had on my table were seen by Virgo as well as LIGO. So, let's see, data from Hanford, from Livingston, and Virgo. So at the bottom, we're plotting the strain as a function of time. And this happens quite fast. This is all over in about 1/10 of a second. So you see, if you can see them, the red oscillations have a lot of noise. That is the observed data. And then the smoother curve corresponds to the best fit using general relativity. And the same is true at the other sites. Coming up, we're looking at the frequency as a function of time. This is a chirp. Relatively weak signal over here seen by Virgo. And then finally, the top set of figures gives the signal to noise ratio. So at the time of the chirp at Hanford, signal to noise ratio was about 7. At Livingston, it was about 14. At Virgo, where they got a considerably weaker signal, it was about 4. And again, one can plot the location on the celestial sphere as to where these 5 events occurred. So they're spread out over a fairly large region of the celestial sphere. But the final black hole merger, which was also seen by Virgo, look how much better it is localized. A much smaller spread over the celestial sphere. So I mentioned that the last signal seen was due to the merger of 2 neutron stars. So this is an animation. These are the 2 neutron stars, with one of them being a pulsar, giving off flashes of light, which you see. And as they come together and merge, you see much stronger gravitational waves. You see some fireworks. And then eventually it coalesces into a single object. So here they're assuming that single object is a black hole. You can see sort of the residue material which is spinning around it. So we'll go through it once more. The 2 merging neutron stars. As they merge, things become more and more violent. Gravitational waves become larger and larger. Electromagnetic activity picks up considerably, and then it coalesces into a single object, which perhaps is a black hole.
So pulsar and neutron star are distinct.
Well, pulsars are neutron stars. Not all neutron stars are pulsars. Well, to be a pulsar, we have to see the beam of radiation sweeping past the Earth.
Okay.
So there may be many neutron stars which have that beam of radiation, but it simply misses the Earth. And so we don't see it as a pulsar. Okay, this is an artist's drawing of what it might look like if you were up close, where you never want to be. If you were close enough to see it like that, you would be very dead. Even many millions of miles away, you would very quickly be dead. But there's a lot of electromagnetic radiation given off over the full electromagnetic spectrum, and this has been studied from Earth, and they've seen a lot of things. Like in the visible and infrared, they've been able to see spectral lines of a lot of new elements which have been created, including some of the heavier elements, and that was mentioned earlier today. I'll say a little bit more about it later. This is the data from the neutron star merger. So as a function of time down here, this is, and let's see, we're plotting frequency vertically here, time horizontally. This is the chirp. And so that happened, the merger happened right where this black line is. Fermi, GBM, Fermi satellite gamma ray burst monitor picked up a burst of gamma rays 1.7 seconds later. And that is correlated, is coming from the same event. This is the first time that any electromagnetic disturbance has been seen from a gravitational wave source. And so this helps us localize where in space this happened. So from Fermi itself, we can localize where the gamma ray burst came from in this dark blue region. There's also IPN, the interplanetary network of other gamma ray telescope, which localizes it within this light blue band. LIGO by itself can localize it within the light green band here or down there. And then LIGO plus Virgo can localize it within this much smaller dark green area. It corresponds to 28 square degrees. We know this event happened 130 million light years away. So it's way beyond our Milky Way galaxy. It has to be in another galaxy. And in this dark green region, there are about 50 other galaxies. So immediately astronomers all over the Earth started using a variety of telescopes looking in that region for the 50 galaxies that are there. And 10.9 hours later, it was discovered. It was discovered in NGC 4993, I think, and discovered by telescope SWOPE. It's a 1 meter diameter telescope down in Chile, and here's a picture it took. What you want to do is compare it with pictures taken before the merger. This is one taken 20 and a half days prior to the merger. And the new feature which you see is indicated by the tick mark there, if you can see it. So that is the afterglow of the merger of these two neutron stars right there. And the same tick marks down below show nothing in that region. So something like 70 telescopes on Earth and in space witnessed this event and studied it. And so here we have some space telescopes and a variety of telescopes around the Earth. So here's Hawaii, that would be Mauna Kea and the Keck telescopes. A bunch of telescopes down in Chile, Southern California, like Mount Palomar, telescopes in Arizona and New Mexico. One of these has got to be the Green Bank telescope in West Virginia. Down here is Puerto Rico, that would be the Arecibo telescope. Europeans have 2 observatories in the Canary Islands. That would be there, and so forth. So this has been very thoroughly studied. This is a picture of that galaxy, NGC 4993 in the visible. And if you look carefully, this little spot of light right there, that's it. That's the glow of the neutron star merger. In the visible, it was originally bluish in color, and then fairly quickly over a few days, became more and more red. So Jim Shedlowski gave this to me to show. This is a slide showing you the periodic table of all the elements, and according to different colors, probably the source of these elements. So the Big Bang generated hydrogen and helium, just a little bit of lithium, and the blue colors that you see here, they were generated, for example, by exploding massive stars. That'd be a type 2 supernova, exploding white dwarf, type 1 supernova. But it is now thought by a number of astronomers that these emerging neutron stars can generate a lot of the heavy elements. So this is the yellow color, and you see that, for example, in gold, both the yellow, platinum, uranium, and so forth. This is still a project of considerable research. Calculations are being done, observations are being made. It's now thought by many that perhaps neutron stars colliding, as we've seen, may generate a lot of these heavy elements which we have here on Earth. So this again is the same kind of picture I showed before, except now we've added neutron stars down here at the bottom. Most neutron stars have masses between 1 and 2 times the mass of the Sun. This merger, which was just seen, has produced something in this vicinity. They put a question mark there because they don't know if it's a neutron star or a black hole. Okay, so I showed you this once before. These are the signals from the 5 black hole mergers which we've had. This last one down here, gravitational wave, seen on August 17, 2017. Let me show you what that looks like. So there it goes. And it very quickly runs right off the end of the graph, so you have to keep stretching the graph. So there we are now, there in 10 seconds. And so this is being compressed as we go to longer times. You can hear this as an audio track. You can hear the humming as the frequency is going
In
up.
real time?
This is real time down there. This is 30 seconds now. Now here's something else that will knock your socks off. During the last 50 seconds of the data recorded, this was radiating, the gravitational waves were carrying away energy corresponding to not just the luminosity of our Milky Way galaxy, but 1 billion times the luminosity. Here it comes. Wow. Merger of neutron stars and the energy being radiated in those gravitational waves, 1 billion times the luminosity of our Milky Way, all 200 billion stars in the Milky Way. Okay, so I've got like 2 minutes left. So can I get an additional 5 minutes? I can finish in 5. Okay, so this just says, this is things I've talked about. There's strong evidence now that these short gamma ray bursts are due to neutron star mergers. We saw it for that last gravitational wave event. And there's good evidence that neutron star collisions may be a major source of heavy elements in the universe. So I'm going to give you a quick tour of LIGO Livingston. This was a tour that we had 13 months ago on October 4th. I was accompanied by Dr. Ismar Santora, retired vascular surgeon from Phoenix. He and I have done quite a bit of traveling together around the world looking at telescopes. And I'd like to take him along because at my advanced age, you never know when a medical emergency. And Dr. Santora is well versed in emergency room procedures. And he assures me that whatever happens, he'll take care of me.
Jesus.
So, Amber Stuver was our tour guide.
Philly is fog and fast.
So this is an aerial view, looking down. So these are the 2 arms, 4 kilometers in length, 2.5 miles each. This is the central building where the laser is, where the beam splitter is, where the control room is located, and so forth. The picnic area here we just covered. There's a little lake here with a fountain. I'll show you that up close. Here's the road coming in. Speed limit 10 miles an hour with big warning signs. No rapid acceleration or braking. Travel at a constant speed, 10 miles an hour. This is the parking lot. This building is a museum or science education center. They bring in quite a few school kids to see it. Let's see, there's a road right here. There's a road which goes, there's an overpass over this arm right at that location. I'll show you a few pictures taken from that overpass. So here's where we stayed the night before. You can see we're down in the tropics with the palm trees. This is the entrance, LIGO, Livingston Observatory. And now we're on the grounds. So this is the central building here. This is our lake and fountain, covered picnic area. This is the Science Education Center for LIGO. Very, very interesting museum, lots of things to look at. This is the original mirror that was used 2002 to 2010, about 10 inches in diameter. So it looks like glass because you can look right through it. Amber assures me that for the infrared frequencies they use, it's a very good mirror. This is a technique they use now to support the mirror. It's a 5-stage process to isolate the mirrors from any vibrations in the ground. One corner of the control room, another corner of the control room. Some of the monitors on the wall. Wide angle view of the control room. Now we're outside. So this is one of the arms coming out, and this is that overpass that goes over the arm. So this is Dr. Centaura walking up on the overpass. Dr. Centaura posing for a picture. So the central building is here behind us. This is one of the arms coming out. The second arm is going off here at right angles. Dr. Centaura posing again, looking the other direction, about 4 kilometers down to the end.
What's the length of that?
4 kilometers.
4 kilometers. Each arm is 4 kilometers in length. What you're looking at, this is a concrete structure, which you see here, to protect a stainless steel pipe 1.2 meters in diameter in which the laser beam is traveling.
Now that's the source of the laser. Do you mirror it at the other end?
Yeah, mirrors at the other end.
Okay, so it goes back and forth.
The light bounces back and forth between 2 mirrors. The distant mirror is way down there. I couldn't even see it with my naked eye. Another picture. This is zooming in a factor of 10 with the camera.
Jerry,
Yeah.
is it accessible? Can a mechanic or technician get inside of that tunnel to a certain?
Oh, they certainly can, right, and they do. They do when it's shut down and not operating.
Yeah.
This is a 15 zoom. And this is the end of my presentation. Well, this is Amber again. She's very generous. She spent 3.5 hours with us and took us on a very extensive tour. Okay, thank you very much for your attention.
If you have a civilization in that galaxy, what is your problem? Is there one? Would something happen from that?
I don't know how many light years you have to be away from that neutron star merger to survive.
I'm wondering about that.
Yeah, I don't know. You can
Because there's a
certainly do a
gamma
calculation of the power that was emitted in the electromagnetic blast. You certainly wouldn't want to be within a few light years, I'm sure.
We're a few minutes past 10, so let's take one more question.
One, yeah, John.
The amount of space grew and shrank was thousandth of a proton,
Yeah.
a billion light years away. So
Yeah.
if you were a few million miles away, 93 million miles away, like the sun distance,
Yeah.
would the Earth be enlarging by miles instead of?
Well, it's a calculation one can do. It's certainly very much larger than it is at a billion light years where we are. I don't know the answer to that, but we can do the calculation.
Okay.
Because, you know, the intensity of the gravitational wave goes like the square of the amplitude, and the intensity falls off as 1/r squared, r being the distance. So it's an easy
So a billion light years squared.
We can do it. Okay, thank you
Okay,
again.
one more question. We did have one hand in the back.
Okay, one more.
What's the size of LIGO compared to the Large Hadron Collider?
The Large Hadron Collider. That's a few miles in diameter. So I think the Large Hadron Collider is larger in size, somewhat. 50 kilometers around. Okay, so that's 30 miles around, and so the diameter is 10 miles. Okay, so that makes it somewhat larger than this. But
All right.
Thank you.